Afternoon, everyone. I know you're quite keen to go get your lunch, so I'll try to keep within the time constraints. My title today is a QPO in the optical polarization of PKS 2155-304. Most observational astronomers have their favorite object, and this is the one I've been working on for the last 2 or 3 years. My work was done in conjunction with René Kraan-Korteweg and Russ Taylor, and then we also have a collaborator, Stephen Potter. This is the wrong one. Right, so I will basically be reporting on the discovery of the first quasi-periodic oscillation in the intraday polarization degree of this active galaxy. And the other thing that's significant for us, for our observations, is this was the first simultaneous optical polarization and very high energy gamma ray observations, where we define VHE as photons with energies exceeding a few GeV. That was obtained for the source during an active or high state. Just an overview of the source. 2155 is a radio-loud AGN, which has its jet aligned with the observer's viewing angle, which was very nicely explained yesterday by Bindu. And this is a very similar diagram of the one that she showed us. So we're viewing straight down the jet. And the emission properties is that we see incredibly bright and highly variable emission, ranging from timescales as short as a few minutes in the gamma rays to scales as long as a few years at optical and radio energies. Generally, what we see is a broadband emission, a broadband continuum that is driven or can be described by non-thermal emission processes. And we also observe polarization at optical and radio frequencies. And it's on this last aspect in particular that I will be focusing. Right, so how can we use the polarization? I think Denise and both Bindu might have mentioned it yesterday. And what it comes down to is that in the optically thin regime, the polarization can be used as a direct indicator of the state of the magnetic field in the emission region of the jet. And we looked at the polarization in optical with an instrument known as the high-speed photopolarimeter, or the HIPPO, stretching the acronym there a little bit, but it sounds a little bit nicer. And this source was monitored intermittently between 2009 and 2012, but in this talk I will be looking at some interesting results from July 2009. So the intraday variability during this period was monitored for about 9 hours over a period of 3 days between the 25th and 27th of July. And we used a temporal resolution of 5 minutes. So we sampled the polarization every 5 minutes. And this is a factor of 3 better than the most recent studies of this object have presented. Now, because we're looking at such a smaller temporal resolution, we are actually able to sample smaller amplitude variations in the polarization degree. The other exciting thing that happened during our observations is that we had measurements that overlapped with the HESS, which is the high energy stereoscopic system, which is this nice, very high energy gamma ray telescope that's situated in Namibia. And they monitored the source from the 19th to the 17th of July. And if you look at the diagram over here, these gray points are the HESS flux sources, and then we have, this is the mean daily averages now, sorry, the daily averages. So we have the gamma ray flux, and then we have over here the polarization degree. What immediately stands out is that we have in the gamma rays 2 flaring periods. This one is a clear flare, and it precedes our measurements here. And then we have what appears to be a developing flare towards the end of the observation run. Unfortunately, that's as much data as we have for that period. So we can't really extrapolate from that anything else or make any definite conclusions. However, continuing onwards, when we look at the mean daily optical polarization of the source during this time, which is given in this table over here, we notice two very interesting things. We see that during this increase in gamma ray activity, we see that the polarization degree, which measures the fraction of polarized light compared to the total intensity, it doubles roughly from 4% to 8% over a minimum time scale of 2 days. And the angle of polarization goes from roughly 90% to about 70%, and that actually changes within 1 day. So clearly there's some interesting event going on here. Moving on to the intraday variability. When we inspected the intraday variability of the polarization, what we saw was what appeared to be some sort of small amplitude modulation that superimposed on the polarization degree like throughout the night. And another interesting thing is that this amplitude modulation occurred at the onset of that second flare over here. So right at the start of our observations, when we looked at the intranight variability, what we see is what looks to be like a quasi-periodic oscillation. When we compare the variability of the polarization degree, however, with the polarization angle, there's no apparent, at least with the eye, modulation that you can see in the polarization angle. And I'll go a bit more into that in the next slide. Now, to test for the presence of any quasi-periodicity, we performed the classic Lomskagel periodogram, which is shown in this figure over here. What we basically see is the power normalized to the variance of the light curve as a function of frequency. The solid markers indicate where the independence of the Fourier frequencies are, and the solid markers, the markers, yes. And then the solid line shows you the oversampled periodogram. And that just means that instead of just using the Fourier frequencies, we oversampled those by a factor of 10 so we can increase our sensitivity to power at the smaller frequency resolutions. What immediately stands out is that we observe these two quite prominent peaks in the periodogram. And so if we classify that as the primary, because it has the most power, and then this one as the secondary, we find that the period of the primary corresponds to roughly 30 minutes, while the secondary corresponds to roughly 13 minutes. That's very close to being a multiple of the 30-minute one, but I mean, it isn't, and it's also not a multiple of the Nyquist frequency, because we checked that. So it appears to be something that is, at least in the periodogram, that is there. When I compared the peak values with what is expected for a white noise spectrum, I find that only the primary peak is statistically significant, and that dotted line just gives you the 95% confidence level for white noise. Of course, this is also the assumption goes in that we can use white noise as a comparison. The interesting thing also, though, to note about the period of these components is that they're very similar to a 15-minute optical QPO that was reported for the Blazar S50716 plus 714, which was reported by Rani et al. In 2010. And that was the shortest optical QPO that has been seen thus far. And that was in the optical flux. Right, so just as a sort of sanity check, what I did was, instead of looking at the polarization degree, let's do the periodogram on the linear polarized fluxes. These are represented by the Stokes Q and Stokes U parameters. So Q and U just measures how many photons of the beam that you're seeing is in the Q projected direction of the wave and how much is in the U projected direction. I wouldn't worry too much about the details of that. Just the point is that it measures the linear polarized flux only. And the reason I did this was because the polarization degree is a fractional value. It is polarized flux over total flux. So, I mean, there could be no modulation in the polarized flux. There could be some in the total flux. And the polarization degree would still show an amplitude modulation. So this is what I mean by like sanity check. When we do the periodogram for the Stokes Q flux, what we find is, even though it's, again, not statistically significant, we find the same two prominent frequency components at exactly the same frequency or period that we observed for the polarization degree. However, in the Stokes U parameter, we don't see any prominent peaks. And this can be explained by looking at how the Stokes parameters is actually projected onto the sky plane. So if you look at the polarization angle, you see that it oscillates near a value of 90 degrees. If you look at the Stokes parameter, so this is the plane of the sky, that's just the polarization's position angle as we see it. And if you have anything that's emitted near 90 degrees, what you're basically seeing is only Stokes Q parameter. So, I mean, there could be a QPO in the polarization angle too. It's just that due to projection effects, we actually don't see it. Right. The nice thing about having this projection effect, though, is that it excludes instrumental origin for the QPO, because if it was the instrument, it would modulate both Q and U components in the same way. So that does seem to point to an intrinsic origin for this polarized QPO. And I'm just going to briefly sort of go over what the origin for this is. I'm by no means an expert, but we do have one sitting in the room, Bindu. So maybe she can help if there's any questions. But the simplest way to produce a polarization QPO in blazars is to have an emission feature that is propagating in a helical magnetic field. So this picture was taken from Marche et al., where they actually observed a change in polarization degree and polarization angle for a feature in the radio and optical polarization, but that happened on a timescale of a few months. And if we do have a helical field, then you'll have a streamlined path that traces a spiral like that, which has a bit of a bigger pitch angle than that of the underlying magnetic field. Not quite sure what the details are, but that is the sort of framework that we're working in. And the timescale of our QPO would then constrain this region to be less than 10 to the 15 centimeters, which is like a milliparsec, which is very small. They also see that the polarization angle undergoes a periodic change, which we do not see. And they see that halfway through one cycle, the polarization degree drops to a minimum. We can't really say anything about that because we don't have EVPA or polarization angle information for that. So that's what that black comment basically says. We have the time scale, it's intraday though, and our EVPA or polarization angle does not demonstrate cyclic modulation, but that could be due to projection effects. I would just like to end with, I'm going to skip those other two origin of QPO slides, but I would like to end with, even though the origin for blazar QPOs is an open question, if we do have a polarized QPO, at least what we know is that for blazars, then the source of the emission must be in the blazar jet. So it's at least constrained to the jet. You know, the jet is massive, so we don't know where in the jet exactly, but we know it's somewhere in the jet as opposed to coming from the central engine area, which is the accretion flow. The other question that comes up is if this QPO is associated with a rise in gamma ray activity, and this is something we still have to look at in future by coordinating polarization measurements or polarization campaign on the intraday scale with gamma ray variability as well. But if this is the case, because we do see on the daily scale, the polarization degree and the gamma ray flux appear to be correlated, then it would suggest that the QPO is part of a longer lived phenomenon in the jet. And I'll end my talk there.
Thanks very much. Questions?
Hi. So I guess this is sort of an obvious question, but for any of these kind of results, you know, the Blazar variability or AGN variability in general is not white noise. It's red noise. There is more variability at longer time scales. So it will be, you know, more appropriate to test compared to a red noise, and also maybe choosing the power spectral slopes, a range of slopes, and also maybe a break in the power spectra, because break causes an envelope on the light curve, which may also give rise to some sort of periodic behavior. So has there been tests with red noise?
So one of the major sort of limitations of the measurements that we do have is that we don't have a lot of a very nicely sampled light curve, so to say. I did go ahead and look at the power spectral density, which is where you fit the red noise to your data. So you do have power law noise, and then you try to see if it's significant compared to that. And this is what I found. Those will be my data points. That's the fitted model, which is red noise, and then that is the 3 sigma of the red noise. But it's not corrected for model uncertainty, because I have so few data points, I can't get a very accurate model for that. So that's sort of the predicament that we're in.
Yeah, no, I was not saying that you calculate the, yes, that's something that you can do, but I'm saying just assuming that there is some you know, red noise spectra with some slope, let's say minus 1.5, something of that order. And then when you test the significance of your periodicity, instead of using a white noise as your random sample, why don't you use a red noise as your random sample? And maybe even add a break to the noise, because that also causes periodicity, so that you can, your significance is, you know, more well tested.
Change with the noise spectra. Yeah, that's certainly something that I'll look at. Thank you.
We can have a few more questions, but I'd like to make one comment, which is that Rama Prakash at the IUCAA in Pune has recently, a few years ago, designed a very powerful optical linear polarimeter, which you can use for doing this sort of observations with single observations. You normally have to, with polarimeters, do some rotation on the instrument in between. And right now he's planning with Stephen Potter at SAAO to build and take an instrument that could be dedicated pretty much full time to this kind of work, and that would be hugely successful, hugely beneficial in this sort of thing. Thanks. There were some other questions? Yes?
Yeah, I certainly agree with Ritvan that can you hear me?
No, we can't. Thank you.
Hello? Okay, so I certainly agree with Ritvan that yes, the significance of, since it's not only white noise which is present in the data, of course there is red noise, and the significance has to be tested, and if the data is unevenly sampled, we could certainly run simulations and check that. But yeah, for the possible mechanism, of course, you see periodicity apparently in your data, and that stands out of your observational uncertainty, but the time scale is very short, I believe. So, and since it's a polarized, it's the variations in the polarized emission that rule out the origin from the disk, because it has to be via a synchrotron mechanism, otherwise you don't see any polarimetry variability. And then I believe that, I mean, of course, from the light curve, I can say that it will not cross the 3 sigma line of the significance. This is one thing. But let's assume that it is there. Of course, it is not significant. Then I believe that it's something related with the turbulence in the medium, and then some shock passing through that. That's what I think. That's
yeah. Okay. I mean, also just if you look at what the Marche paper found in 2008 for their sort of helical field.
No. There you expect to see much longer timescales.
Yeah, so that's what I was going to say, because then you expect much longer timescales than what we're seeing. So it probably points to more.
It's a very tiny fraction of your jet, what you are seeing here.
Sorry?
It's a very tiny fraction of your jet, what you are seeing here.
Yes, yeah, I agree.
Okay, I think we'll have to stop there because otherwise we won't have any time for lunch. But please can we thank all these speakers, this morning's speakers again?